Hi, everyone. Welcome to the 72nd session of the MedAI Group Exchange Sessions. So this week we have Karan Singhal from Google Research here with us to speak about their work on large language modeling for clinical applications. So very exciting topic. This is actually Karan's second time here at MedAI, and we're very happy to have you back here, Karan. So Karan co-leads teams at Google Research and works on medical AI, foundation models, representation learning, and federated learning. He's broadly interested in developing and validating techniques that lead to a wider adoption of safe and beneficial AI. And before joining Google, he received his master's and a BS in computer science from Stanford University. So thanks so much, Karan, for joining us today. And as we kind of just chatted before this session, we'd like to keep the session as interactive as possible. So audience, feel free to jump in if you have any questions. And without further ado, let me hand it over to Karan.
Thank you so much, Nandita. Yeah, I'm happy to present this to this group. So this is our recent paper, Large Language Models Encode Clinical Knowledge. We put out a preprint for this a couple months ago, and I'm very happy to be presenting. And like Nandita said, feel free to jump in with any questions as they come up. So agenda for today, we're going to be talking through introduction for the paper, and then kind of the key contributions of the paper, the results, and some of the limitations and considerations that we had as well. As an introduction, so I don't think it's super new to this group that language is a pretty important part of medicine. Language enables the key interactions, crucial interactions between clinicians, researchers, and patients that can often change lives. At the same time, human AI collaboration in different kind of forms has been emerging as an important aspect of kind of more useful, responsible, and reliable AI systems. And language has been an important medium for that kind of collaboration. However, in the medical domain, especially in terms of models that are being used in the real world today, a lot of models are kind of narrow single task systems like classifiers or regression models. And these models aren't often always fully utilizing language in the way that you'd hope for. At the same time, we have all these recent advances and excitement around foundation models. And foundation models, especially large language models in particular, use language as a tool for mediating human AI interaction. And that interaction can happen through the outputs of the models in terms of text that they're outputting, but it can also happen through feedback that humans can give these models as well. These models can also generalize and be repurposed kind of easily across domains and tasks, including the medical domain. The few-shot learning paper was a great example of this with GPT-3. In this setting, also, they can also encode and retrieve from large-scale medical data, and that's one of the kind of things that we showed with our paper. We also argue that they can manipulate knowledge, so not just retrieve knowledge, but also use that knowledge to kind of form conclusions and do multi-step hops of reasoning, produce explanations, and also provide estimates of uncertainty, which are all seemingly important in the medical domain. And also foundation models in general beyond LLMs can also extend to other modalities beyond text, offering for future promise as well. And so I think all these advances really offer us an opportunity to rethink what we mean by medical AI and what that could look like. At the same time, there's been a lot of previous work on LLMs for science and biomedicine just in the last year or two. And so just in the last year, there's been really an acceleration of papers that have done things in the realm of science and biomedicine, not super always focused on kind of clinical outcomes or clinical knowledge, but this is kind of a background for our work. So what's missing from the literature today? I think the first and most important thing really is kind of safety and reliability. These large language models in this setting are often producing hallucinations, are kind of amplifying biases, otherwise misbehaving, not reasoning properly. This really, really matters in the medical setting. And so studying safety in this setting, I think is really, really important. Secondly, we don't have a standard set of benchmarks for evaluating whether these models are containing clinical knowledge in a useful way. And there's a lot of things that you could study with benchmarks, but it's unclear what is a comprehensive and complete set of benchmarks. And third, this setting is really, really safety critical. And so we can't just rely on automated metrics like accuracies or blue scores and things like that to be able to do our final evaluations. And so we really need to think about what is our evaluation framework, what do we really care about, and how do we get humans in the loop so that we can actually measure progress and mitigate harms. So now I'll go a little bit into the tasks and data sets that we use for the paper. So in this paper, there's a lot of things that we could focus on in the world of medical AI, but the thing we focused on as kind of starting point was medical question answering. Answering medical questions is a fairly hard task. It requires the ability to kind of comprehend the question, especially if you're talking about a wide range of medical questions. The ability to comprehend the question, the ability to recall medical knowledge that might be relevant and pertinent to the question, and also the manipulation or reasoning of that knowledge to kind of come up with a final answer. And so one of the contributions of this work was this MultiMed QA benchmark, this medical question answering benchmark, which combines together 7 different data sets, 6 of which already exist, 1 which we contributed ourselves, towards a kind of unified benchmark for medical question answering, which aims to resolve some of the limitations of existing kind of benchmarks and data sets. At the same time, we were really thinking about how do we move beyond multiple choice accuracy or generation metrics like BLUE score. So in particular, MultiMed QA does include long form answer questions, and we'll be talking about human evaluation results on those as well. It does include multiple choice questions from varying medical exams or medical research questions, includes some open domain questions, some closed domain. And so there's a wide variety of questions that are kind of being asked in this benchmark.
I had a quick question actually. So is it the case that the target user is a clinician, or are you expecting questions like even from like non-clinical folks, like maybe people who are surfing the WebMD, and what's the target?
Exactly, yeah. So both. So we both have like professional medicine questions as well as consumer medical questions. So 3 of the data sets that we were looking at, the medication QA, health search QA, and live QA, were consumer medical questions that were submitted to Google or other places, and we basically evaluated on those as well.
Gotcha. Thank you.
Yeah. Any other questions?
Yeah, I got a question about these 7 data sets. What's the format of these 7 data sets? What's the, what kind of questions, what kind of answers?
Yeah, absolutely. So let me show some examples of some of the questions. So some of them were kind of free response questions. So like the health search QA data set, which is commonly searched questions on Google, are questions that people commonly searched. And like basically like our goal is to come up with a long form answer. Same for live QA is a similar thing. For Med QA, which consists of USMLE style questions, the kind of questions that people take in medical school in the US for like step 1, step 2, step 3. These are multiple choice questions that often look like clinical vignettes. So like the example shown here, and then a question about that clinical vignette that often requires both kind of retrieving knowledge. So understanding the question, retrieving knowledge, and then kind of doing potentially some multi-step reasoning potentially based on that. And so these are multiple choice questions as well. Does that help answer your question? There are also other data sets, but these are a few examples.
Yeah, and that's good. Thank you.
Yeah. Cool. Moving on. So this is just a summary of the MultiMed QA data sets. Again, this is 7 data sets. A few of them are multiple choice. A few of them are long form answer. There's different sizes. There's different. Some of them have answers included. Some of them don't. And you can see they have kind of varying domains. And so we're aiming for really a broad coverage of different aspects of these data sets. Cool. And the next thing we wanted to do is really be thoughtful about the framework for human evaluation, even before we start the
Karan, can I ask you one quick thing? So actually you mixed all the 7 data sets together for model training, or you are training the model separately on each of these data sets?
Yeah, it's a great question. I'll talk a little bit more about training later, but what we ended up doing was kind of the mixing.
Okay, so mix all the data sets together, right?
Yeah, so in particular, we mixed data sets for the consumer response question data sets together for this technique that we developed, which I'll describe a little bit more later.
Okay.
Cool. So again, we really want to be thoughtful about the framework for human evaluation, and we want to think about it before we even start the modeling work. And so we really want clinicians in the loop for this, because this is the kind of thing where you really need their feedback to be able to make kind of meaningful conclusions. And so we came up with these 12 axes, partly derived from previous work around what could be important to evaluate in terms of the long-form responses to consumer questions that these models might output. And so these are things like scientific consensus, or whether there's harm or likeliness of harm, whether there's the comprehension, retrieval, reasoning that I've been talking about, and then whether there's any inappropriate or incorrect content, like sometimes a model could be quite detailed and there's evidence of correct retrieval, but there's also evidence of bad things. Is there anything missing? Is there any possibility of kind of bias towards specific demographics? And then on kind of the non-clinician side, on the non-expert side, we also asked lay users, kind of regular people like you and me, whether the answer is relevant, whether it captures their intent, whether it's helpful. And so based on this, so we had like some iteration on this protocol as well, where we kind of worked on it by kind of consulting different kind of stakeholders. We also refined it based on having kind of triple ratings to kind of understand the variability of ratings. And then finally, when we want to do the final ratings, we asked 9 clinicians based in a bunch of places, UK, US, and India, to kind of perform these ratings across all these different axes. So for each of these axes, they might have 3 or 4 options, like likely harm or severely likely harm, things like that. Next, I wanted to talk a little bit more about kind of the modeling efforts that we did here. And so I think there's a lot of work that can be done. There's been a lot of work kind of showing that large language models in general, if you kind of few shot prompt them or things like that, they can often do fairly well across a wide variety of tasks. For us, I think we thought we had a unique opportunity to kind of think about like thoughtfully, like how do we better align these models to the medical domain beyond kind of prompting strategies. And so I'll talk a little bit about kind of the prompting strategies that we talked about, as well as kind of the techniques that we did to kind of go beyond that as well. So for a little bit of background, a lot of this work is built on the kind of pathways language model, or PaLM. And so this was released last year as a kind of large language model with 540 billion parameters trained using this pathway system. Basically, this model was shown to perform quite well across a variety of NLP tasks. And it was trained across a large variety of tokens, a multilingual corpus. There was some vocabulary improvements over previous models for things like math, encode, and reasoning. And there's been kind of follow-up works like Minerva kind of showing those improvements in kind of exam type questions. And there's different variations and different sizes of PaLM as well, which we kind of talked about in our work as well. And at the time, this model achieved SOTA on pretty much a wide range of NLP tasks, including multi-step reasoning tasks, which was a kind of thing that models at the time struggled quite a bit. I mean, continue to struggle with, but at the time there was not much progress at the time. And also did quite well on the Big Bench benchmark. The next model that we wanted to kind of talk about for context is a variation of PaLM called flan PaLM, which is basically an instruction-tuned version of PaLM. So this is PaLM, where we do some additional instruction tuning afterwards. I'll describe instruction tuning a little bit more in detail later, but basically instruction tuning is a variety of fine tuning where across a bunch of NLP tasks, you provide some instructions and say like, hey, model, do this, and then tell it to do that, and then do that for a wide variety of NLP tasks, so that the next time you give it instructions, even if they're not instructions that you've given it before, it can do well across a variety of tasks. And so this I would put as an example of like instruction fine tuning in the same way that like Instruct GPT is kind of doing an approach like that. This model also reached SOTA on several benchmarks and improved on PaLM in a lot of ways. And so I think, like I kind of alluded to earlier, I think there's going to be 2 kind of classes of strategies that we explored in this work. One is prompting strategies. So on top of flan PaLM, can we do things like few shot prompting or chain of thought prompting or self-consistency prompting, all of which I'll describe in a second. And the goal of which is to adapt to these diverse tasks without doing a bunch of parameter updates. Secondly, we want to do prompt tuning, which is, I'll describe again, and I'll link to a paper as well. But this is a inexpensive, but also gradient-based parameter updates, where you don't train the whole model, you train just a small part of the model and reuse the whole kind of foundation otherwise. And then you use that to learn soft prompt vectors. So instead of putting in a hard prompt like specific text, you learn like some soft prompt, which is like this learned embedding. And the reason why we have this focus on data efficient alignment strategies in this work is because in the medical setting, there isn't a lot of high quality data for us to be able to train on. And so it's really important for us, and it's also quite expensive to collect high quality data. And so we can't collect 780 billion tokens of high quality medical data, right? And so we need to be able to learn quickly and efficiently from limited data and use that to kind of improve our models in an effective way. So for a little bit of context on few-shot prompting, this is maybe familiar to many folks. This is from the, I think, the GPT-3 paper. The basic goal of few-shot prompting is in the prompt to the model, or in the kind of input you give the model, you give it a few examples of the thing that you want it to do. And it turns out this kind of lets it know exactly what you want to do and what the formatting of what you want is, and helps it perform quite significantly better than if you didn't do this. So this is kind of like a baseline, kind of strong baseline that like any kind of LLM applied to any tasks will generally be doing. Please feel free, I'm going to describe a few different methods, and maybe one or more of them is unclear, so feel free to stop me at any time. So the next one I want to describe to you is chain of thought prompting. And so chain of thought prompting, so on the left we have standard prompting, where you basically, again, this is an example of few-shot prompting, where this is a one-shot before the question and that we're asking the model. And in standard prompting, what we're doing is we're asking the model directly for the answer. In chain of thought prompting, we are giving the model an example of a reasoning path or kind of a chain of thought that the model can use to kind of condition on. And this basically induces the model to produce an explanation or a multi-step reasoning path for the question that you're actually asking it. And so basically you can view chain of thought as a version of few-shot prompting where you ask it to produce an explanation instead of just the answer. And there are a couple nice aspects of this. The first is that you get the ability to get an explanation from the model, right? So you get the ability to kind of double check what the model is saying. Often it's easier to double check whether the model is making sense or not if you actually have an explanation coming from the model. And so that seems very nice, especially in the medical setting. The second thing is that this actually improves performance. And so this is kind of an interesting quirk of these models, that they don't seem super good at this multi-step reasoning within like one generation of token, within like a short sequence of tokens. But if you do this over a longer sequence of tokens, you have the model conditioned on those previous tokens in terms of those previous generations, then the model gets significantly better at doing things like math problems or reasoning problems or things like that, which previously these models struggled with quite a bit. Any questions on this? This might be new to folks.
Yeah, I actually had like two questions. So the first one is more about the chain of thought prompting itself. So is this typically done only during training, or is some version of this also done during inference, like to basically get a better answer? And the second question is, so if you're adapting chain of thought prompting for the medical setting, how much domain knowledge do you actually need to prompt it in a way that that actually gives meaningful answers? Because I can imagine if a consumer is doing the chain of thought prompting versus a doctor is doing the chain of thought prompting, like the prompts would look very different.
Yeah, those are great questions. So typically when people say chain of thought prompting, they're often referring to inference. So at inference time, given a pre-trained model like PaLM or whatever, you ask it, like in the context, in the input, you ask it, you give it a few shots where you give an explanation, then you ask it to give an explanation for a new thing. But people also do, and we also did, examples where you actually provide that that path in training, and then you use that to improve the model as well. So that's also something that people explore. And then for the second question, do we need expertise? Yes, absolutely. So yes, getting clinicians from different backgrounds and getting them to provide input was an important aspect of the techniques that we apply later as well.
Got it. Yeah. I mean, later, maybe you might already be doing this, but if you can provide some insights about how to do this prompting, that might also be very useful for all of us.
Yeah, absolutely. There's a lot of like tribal knowledge when it comes to this stuff with prompting. Like there's a lot of magic. So definitely happy to kind of share some of the stuff that we've learned. And I think one nice aspect of this feedback question that you this clinician kind of input question that you asked is that for chain of thought prompting inference in particular, often like all you need is like 3 or 5 examples, because that's likely that might be all that fits in your large language model's input anyway.
Right. So I was about to ask you that. I think chain of thought prompting, another interesting thing is like, what is the optimal number, right? Like that is also difficult to decide, but it seems that there is a universally established number 3 to 5. I don't know, like if you guys face the same thing or.
Yeah, we also did 3 to 5, and I think after like 3 to 5, the benefits tend to saturate, and you're better off using other methods to try to improve performance. Is my sense.
Okay.
Cool. Hopefully that helps. Any other questions on chain of thought? All right. The next thing I wanted to describe to everybody was self-consistency prompting. So this one might also be new, so I'll also stop for questions. And so this is a combination of few-shot chain of thought and then this new kind of majority voting thing, which is basically like the first step you do is you prompt a language model using chain of thought examples. Again, like we showed in the previous slide, like few-shot chain of thought examples. And then you ask the language model to produce multiple possible reasoning paths. So we're asking the model for an explanation or a reasoning path to get to a final answer. And now we ask it for multiple of those instead of just asking for one. And we kind of stochastically sample in some way from the language model to get multiple reasoning paths. And those multiple reasoning paths may lead to multiple answers. And then so the final step is now aggregating over those final answers in some way. And so in this case, we show this kind of majority voting approach where you take the answer that shows up the most often or above 50% of the time or whatever. But we can also do other approaches. Does anyone have any? So the point of this approach is basically the large language model is not, when you're sampling from the large language model, there's been a lot of work showing kind of like the way you do the decoding, or whether it's greedy or nucleus sampling or whatever, it really matters. It can often really matter. And what we're doing here by sampling multiple reasoning paths is kind of marginalizing over different kind of decodes. So instead of relying on just one decode or just asking the large language model once for an answer, we're asking for it multiple times and then marginalizing over all those possible answers. Any questions on that intuition?
I think this is very interesting. Do you see like there could be diverse answers provided by the model, or the answers are usually like pretty consistent?
Yeah, I mean, in general, like for most questions, it tends to be fairly consistent, but there are often cases where you ask it something once, and then it gives you the thing that's less common, the output. So if you want to be kind of fully confident that the model you're getting from the large language, the output that you're getting from the large language model is its best guess, then something like this can often be useful. But for most of the time, this doesn't add that much value. I think it's more of an add-on to chain of thought prompting versus like something that significantly boosts performance.
I see. And how many samples do you usually need to sample to get like a more consistent answer?
Yeah, I mean anywhere from like 3 to, in the paper we did 11 primarily. I think 11, 21 are like common kind of numbers that people use.
Got it. Thank you.
Yeah, I have a question here. So for all these different samples, what part are the prompts and what part are the answers? I'm a little bit confused. So like, for example, you use the C has 16 minus 3 something to the day as a prompt, and then got the answer is 18. Is that correct? Or or the output is C has something until the answer is 18?
Okay, so I'm gonna try to clarify what is the prompt, what is the question, what is the answer.
Yes.
So on the left side it says prompt with example chain of thought. This is a one-shot example where this whole white box is what is input into the model. And so the QA example in the beginning is an example that one shot. And then the next QA pair where the A doesn't have any answer is the actual question that we're asking. And then on the right side are the model's outputs that we sample multiple times. So the green one at the beginning that you talked about is one total generation from the model.
Okay.
Yeah.
Yep. Good. Thank you.
Yeah.
One other question, Karan, if I could.
Yeah, of course.
So I noticed that the samples that you're giving seem to be questions that are, I'm not sure how to call them, but I think of them as being algorithmic questions. Like the arithmetic is an algorithmic question where you could have any numbers and a person would follow the same algorithm to answer it.
Yeah.
Do you think, are many of the medical knowledge questions algorithmic, or are they more facting? You know, like you need to come up with a specific fact related to a disease or something like that.
Yeah, it's a really good question. I think a lot of questions can be like largely more focused on retrieval, but we deliberately selected data sets that also often involve kind of multi-step kind of paths of reasoning, where like you say like, okay, based on the symptoms, based on this person's profession, they may be at risk of this. Based on this, they might have this biomarker. Based on this biomarker, this is probably the result we should see on our test, or things like that. And so we did observe, in general, people have observed with chain of thought, like the kinds of questions where you see the most significant improvement are these, what you describe as algorithmic, like questions where there's like a series of steps and each step is based on the previous one. And so in the intuition there is like the LLM gets the condition on the previous steps when it's doing its next generation. We observed a similar thing in this setting where a lot of the questions that we were looking at are examples where like this multi-step thing helps. And the large language model without this chain of thought often doesn't do as well, if that makes sense.
Thank you. Yes. What percentage do you think of those baseline data sets, question answer data sets, do you think are this sort of algorithmic type versus the more retrieval?
Yeah, it's a good question. I think for a lot of the consumer question answering data sets, it feels like it's a little bit more retrieval oriented. For the example of like the MedQA data set, I think a lot of the questions tend to be like clinical vignettes, and then you have to do like 2 or 3 steps of reasoning depending on the question. I think that's like probably the majority of those MedQA questions. So when we're applying these like chain of thought and self-consistency approaches, where we saw this most significant gain was for that data set. There's another data set, PubMed QA, that we showed earlier. I'll describe some results later, where we actually didn't see any improvement at all from doing this chain of thought, self-consistency stuff. And there, it was basically like retrieving, it was an open domain question answering, where you're basically retrieving from the previous part of the question. There's some context included in the question. There, it felt like it was less useful because it's probably less of a kind of multi-step nature to that. So I think we'll see, I'll present a little bit in the results, but I think the results also reflect like some of the data sets also had this kind of algorithmic nature, some of them had less of it.
Thank you.
Yeah. Cool. Let me keep going. The next technique, which I want to briefly present, is called prompt tuning. This again might be a little unfamiliar, but this is not prompt engineering. This is not like changing the prompt text. This is fine-tuning a small part of the model so that you learn a soft prompt vector instead of like a specific sequence of discrete tokens as your prompt. And so you're basically back-propagating into this specific part of the model to be able to update it. And it turns out that when you do this with maybe 50 or 100 examples, you can often do it almost as well as fine-tuning the entire model. And you can do this in a way that's very computationally efficient. You can reuse basically the entire model. And the same way you kind of input a prompt into the model, you can input this prompt vector. And so you can have this base model, you can have different prompt vectors for different tasks, and you can kind of customize the model to your needs. And so we think this prompt tuning technique, we were excited about this prompt tuning technique for this setting, given the kind of our data efficiency needs in the setting. Lastly, I described.
I have a question about the prompt fine tuning. So you just fine tuning the sub prompt part, is that correct? So for whole model, like the language model part, you just freeze everything and then just fine tune this prompt tuning part, or you also update all the whole language model parameters?
No, yeah, the first thing you said. So you freeze most of the model and you just fine tune the soft prompt part. And the reason for this is to reuse that part. So just as an example, and for this paper, the prompt tuning that we did was over just about 2 million parameters. And the model that we were dealing with was 540 billion parameters. And so that made this kind of training much more kind of manageable.
Okay,
and it also
thank you.
Enabled us to do this with less data. That's another significant benefit of this, that like prompt tuning actually works better than full fine tuning when you have less data.
So for the for this sub prompt, how many of them, how many sub prompt you use for fine-tuning?
So in this figure, this is a figure from the paper. What we actually did was we learned one model, one soft prompt, and then we combined that with flan POM to call that MedPOM. And so basically we had one model that did all the things, if that makes sense.
Yeah, okay, thank you.
Cool, thanks for the questions. And then next we had instruction tuning. I described this a little bit earlier. This is basically fine tuning where you are prepending some instructions to the fine tuning examples. And so you're doing this for a wide variety of tasks and a wide variety of examples. And kind of the goal there is to be able to generalize to unseen tasks and unseen examples based on having this wide variety of tasks that you've seen. And so putting this all together, what we did for MedPOM was basically what we call instruction prompt tuning, which is a combination of instruction tuning and prompt tuning, where we give it a bunch of examples of instructions plus questions plus answers. And then and the answers are coming from clinicians. And then we use those examples for instruction prompt tuning. So basically tuning that small prompt vector using instruction examples. And so we use that to produce prompt parameters aligned with the medical domain, combine that with flan POM, and that's the thing that we're calling MedPOM. Any questions on that?
So sorry, maybe I missed this. Do you use, like, did you mention that you also use chain outside prompting here, or do you just use the prompt tuning part?
Yeah, it's a great question. So in the answers that we're doing here, we do try to provide some kind of like example, like explanation for the kind of the answers as well. We also, this wasn't in our main results, we also kind of in the appendix also included some results where we took multiple choice questions and we also provided explanations for those answers and then also fine-tuned on that. But that wasn't part of the main results. I'll also describe separate chain of thought results on flan POM as well in the results section.
Got it. Okay, thanks. Also, just like there's one question in the chat, but maybe if you prefer to answer it later, that's also fine. So I think someone was asking, what if there's an what if the example chain of thought has logical errors and how would that kind of affect it? And it might be very useful for clinical context as well.
Yeah, this is super important. So definitely in any kind of prompting technique, it's really, or any data efficient alignment technique, it becomes really important that the data is actually quite high quality. If you're including like 3 or 5 examples of chains of thought in your prompt, it's pretty important that those are pretty good examples of examples of chains of thought. And so if you do have kind of errors in those, or if there's other mistakes or retrieval mistakes or whatever, these kinds of things can result in smaller performance. So it's definitely important to kind of make sure that the data is in good shape. Cool, thanks for the question. So I wanted to give a little bit of an overview of the results. So quick highlights. On the multiple choice data sets, we were able to do significantly above SOTA. On the free response data sets, we were able to get MedPOM to produce fairly compelling responses to a wide variety of medical questions. So let me go into those results a bit. And so if we compare our method and previous results on these 3 data sets, these are 3 multiple choice data sets: MedMCQA, which is Indian medical exam questions, MedQA, which is US medical exam questions, and PubMed QA, which is medical research questions based on PubMed abstracts. We achieved state-of-the-art performance on all of them. And these are examples these are the papers that we're comparing against in this. In particular for MedQA, the US medical licensing exam, which we view as a fairly high quality data set among all these data sets. There was a really significant bump in performance above the previous SOTA. And for MMLU clinical topics, which is a subset of this MMLU data set used in other kind of benchmarks, we were able to kind of see significantly above other models as well. One other result I want to share with you guys was we were kind of interested in what happens when you try to understand how well these models encode uncertainty. And so we tried to basically ask an LLM multiple times a question for the self-consistency thing. And then we tried to threshold on confidence based on how often it was saying a given answer. And what we observed is that if we defer based on this measure of confidence, that the accuracy of the model goes up quite a bit. So for example, if you defer 20% of the time based on like a large language model saying that's not super confident according to the self-consistency analysis, then the accuracy on MedQA bumps up from 67 to like 73%. And so this is potentially promising because this suggests that these models are also encoding when they don't know about a question in addition to like the actual answer to the question. And that suggests that like in potential future applications, we can kind of use that to figure out when we should be able to defer to a clinician expert versus like relying on the model.
This is super interesting. Can I ask a question on this one? So, do you still use the same majority vote for like determining if the model is confident or not? Like basically get how many of your results match or are consistent to get the confidence score, or how do you do that?
Yeah, exactly.
And because all of these are like long form questions, or are you doing this on multiple choice? That's another.
Yeah, this is on multiple choice. So this is on the MedQA data set. So there's 4 choices, and we asked the model like A, B, C, D, which is the answer after your explanation. And then we threshold on, did it say 80% one answer or did it say less than 80% one answer?
Gotcha.
Yeah.
Do you have any insights on how you can do this for like a non-multiple choice question? Because then defining consistency might be kind of harder. So just curious about that.
Yeah, that's a super interesting question. I think it's an active area of research, and a lot of people have been producing papers in this area. I think there are simple baselines that we can draw upon. So, for example, we can, in a lot of classification applications, people often use like the softmax probability score. In this case, it's a little bit more complicated to use it because if you're doing a long form generation, there are many tokens, there are many softmax generations. You can still use something like that as a proxy. One thing that people have shown to work actually surprisingly well, and I think this is a quite strong baseline, is literally just asking it, like, how uncertain are you? And it turns out that actually performs well, especially if you tell it to be good at that task via training or via prompting. And so I think that to me is like a strong baseline. That's the baseline to beat.
Well, that's very interesting now. Thank you.
Yeah. Cool. I want to describe some more results on the human evaluation side. So this is with the clinicians. So again, we had these 12 axes for clinician eval and these 2 additional axes for layperson eval. And so one of these axes was alignment with consensus, the medical consensus. And so if we took FlanPOM and we asked clinicians how often was it aligned with medical consensus, they said around 62%. If we ask clinicians the same question and they produce an answer, and then we ask a separate set of clinicians, like, hey, how good did these clinicians do at this? Then they got 92.9. And then MedPOM responses after this instruction prompt tuning technique were able to get to 92.6. So roughly about the same. And then on the comprehension, retrieval, reasoning, we also saw a similar trend where in general, FlanPOM significantly lagged behind clinicians, but MedPOM usually made up most of the gap, but remained kind of generally a little bit less than clinicians. And so for evidence of correct comprehension, retrieval, reasoning, you can see generally a similar story, and similar for evidence of incorrect comprehension, incorrect retrieval, incorrect reasoning, where you want the numbers to go down. You can see again, MedPOM is generally closing the gap at least a little bit with clinicians. Next, on kind of incorrect or missing content, here we actually observed that, especially for the generating inappropriate and incorrect content, that MedPOM did actually slightly worse than FlanPOM. So this remains definitely an area for improvement. I think qualitatively what we observed was that MedPOM answers were really, really detailed, and FlanPOM answers were often like one sentence. And so what happened, I think, was MedPOM answers were often really detailed, but they also slipped up on one of those like 8 sentences that they wrote. And then that results in kind of a higher rating for incorrect or missing content, or inappropriate or incorrect content. But then if you look at the missing content, you can see MedPOM performs more similarly to a clinician.
Do you look at those examples of inappropriate and incorrect content? Because I'm curious, like how inappropriate it would be, and like the potential harm that it could bring to to the patients if this is really being used in a clinical setting?
Yeah, it's a great question. So we did actually explicitly evaluate harm according to these clinicians as well. Qualitatively, generally it was the kind of thing which, like, you could, if you looked it up on Google, you could also come away with that misimpression. Or if you search something, you could often find websites saying that thing, which is like slightly wrong or misleading or whatever it is. So it wasn't like super crazy like stuff. It was more like the kind of stuff you could find, and you have to kind of sift through to understand whether or not it's actually accurate or not. And yeah, so next on kind of extent of possible harm and likelihood of harm, you could see again, flan POM did significantly worse than both MedPOM and clinicians, and MedPOM and clinicians performed more comparably. And next for bias for different demographics, again, flan POM did significantly worse. MedPOM did better, and similarly to clinicians. I also wanted to go through human evaluation results for lay users. So again, this is non-expert evaluation. And so we're kind of more focused on asking about things like relevance and helpfulness here. So in terms of addressing the intent of the question, it seems like, again, we see a little bit of a gap between flan POM and clinicians, and MedPOM makes up most of that gap. And in terms of helpfulness, we see, again, flan POM doing significantly worse than clinicians, but then MedPOM making up most of that difference. Any questions on that, the human eval side?
I had a quick question. So I really like the 12 axes that you kind of coded up before. But I was wondering if like you explicitly check how much hallucination is being done, or is it just a part of incorrect responses? Like, I'm just curious to see what percentage of the incorrect responses are actually hallucinated versus they're just incorrectly retrieved or something like that. And
I see. Yeah, so we didn't have an explicit, like, I guess a little bit hard for a person to tell whether or not something is a complete hallucination out of nowhere versus like the kind of thing which shows up on the internet but like is probably wrong. So it's a little hard for a person to evaluate that even. But yeah, in general, the way we tried to capture this was via this inappropriate or incorrect content. In general, once we did this instruction prompt tuning technique, flan POM initially was often really hallucinating, like out of nowhere. Once we did this instruction prompt tuning technique, it was really not happening in the same way. It was more like the kind of things which are maybe debatable sometimes, or it was like one sentence out of 8 where it said something slightly wrong, things like that.
Got it. Okay, thank you.
So yeah, just as for instance, if you asked it, should I take ivermectin for COVID-19? Would it, because there's a lot of different things out there on the internet, would it just give a high uncertainty, or would it sort of go for what at least most doctors would take as being more definitive sources?
Yeah, this is a super tricky question. I think I'm gonna try it, by the way, after this talk, because I haven't tried it. But I think I think there's a couple limitations here. One, and I'll discuss some of the limitations also in the last section. One thing I'd be worried about there is that these models were largely trained based on a corpus of data that was frozen in like 2022. And so any writing or any knowledge or any scientific research that's come out after that, I think it doesn't even have the ability to kind of take into account. These models aren't actually doing literal retrieval from the internet. They're in this paper, all we're doing is just like relying on the corpus of knowledge that the language model has encoded in itself, which is maybe not the most ideal way to do it, especially when it comes to things that are like changing over time, or like people have different opinions over time. So in general, I wouldn't be surprised if the model performs badly on that kind of question for that reason. And I think integrating retrieval into large language models, especially for kind of high stakes applications like this, I think is going to be an important direction going forward.
Thanks.
Does that help?
Yeah, no, it does. And I'm always impressed. Like, Google seems to do a very good job with those questions for several years. So given that you're at Google, like it gives like that sort of top result. It will pick out something from someone who's what I would at least judge as a doctor is a valid source. Like I just tried it now, and it was like, oh yeah, that's a university website that it's citing.
Yeah, absolutely. I mean, and I think it remains an area of research to be really for our large language models to kind of do that thing as well, like to be able to retrieve from these sources to figure out like what is that summary of content that you see at the top, right? Like what is that concise summary? I think that's something that like is going to be pretty important for large language models in general. You can see it obviously as important for search. And I think it's going to be important for these medical applications where it really matters that you are retrieving the right knowledge.
Thanks.
Cool. Okay, cool. I want to also talk a little bit about limitations of this work and ethical considerations, of which there are many. And so the first one is around kind of basically everything we did in this paper, I think, has significant limitations. So the first contribution we made in this paper was this kind of benchmark MultiMed QA. And while we think it's fairly diverse, especially compared to kind of existing benchmarks, and it contains a lot of things, it's definitely not exhaustive. It's definitely not actually reflecting real-world clinical workflows, and that's a really significant limitation. We focus really on medical question answering, and a lot of the time it's this fairly contrived setting of medical exam questions, or in the US or India or whatever it is. And this doesn't necessarily reflect what real-world clinical workflows look like, right? These clinical vignettes are written for exams. They could be kind of irrelevant when it comes to the real world. And so this is definitely important for real-world research, for future research, to be kind of think about like what are the real-world workflows and what are the data that we need to be able to evaluate in those real-world workflows. Second, there's a lot of LLM capabilities that are kind of missing from MedPOM. So the first one that I was kind of briefly alluding to earlier was kind of grounding or retrieval in real authoritative medical sources instead of just relying on kind of the knowledge base that's stored in the model. And there's also this time-varying nature of medical consensus, which I think was relevant to your question, Chris. And right now, we don't really have any way to deal with that. We're training on this frozen corpus frozen at 2022. And so there's not really a way for us to deal with this unless we are actually being able to do things like have our large language models use search and retrieve from the internet. We also want to kind of explore work around kind of detecting and communicating uncertainty effectively. We did some kind of preliminary work in the space with the MedQA data set, but I think there's a lot to explore here. And I think this, again, is super important in the medical domain, where it's, especially for human AI collaboration, it's really important that the AI knows when to defer to the human. And also, none of this was multilingual. There's many more people in places where there could be a benefit to having these models use multiple languages. And lastly, in terms of human evaluation, there's a lot of these axes which we kind of came up with. We consulted, we did a little bit of iteration, but really there's a lot of this that's fairly debatable. Exactly what are the 14 axes that you want to use? Exactly how you split things up? Do you, as Nandita said, do you think about like hallucination as a separate category, or do you group that into inappropriate content or incorrect content? And also, even once you have the kind of evaluation framework frozen, the number of people we have evaluating the diversity of those people is going to be limited, right? And so there's obviously going to be lots of room for future work in terms of improving that. On the kind of fairness and equity side of things, our evaluation of bias was very, very limited. Basically, we asked a bunch of doctors, is this biased? And then we didn't define what bias means in a very careful way, right? And so this is a really important limitation of this work as well. We didn't really think too much about algorithmic approaches to assess bias. We kind of just asked people. And when we really think about what the use cases that these models can be deployed in, I think it really becomes important to think about like, okay, given this use case, what are the possible harms? And in different kinds of harms, both physical harms, ethical harms, social harms, things like that. And given that, can we kind of think about like, okay, now how do we kind of make this rigorous? How can we kind of come up with some kind of assessment of whether these harms are happening or not, and potentially happening in the real world before we actually do any kind of real world deployment? Any questions there? Cool. So I just wanted to conclude, again, I think foundation models and large language models present an opportunity to rethink what medical AI looks like. I think our research helps kind of provide a preview or a glimpse into like the opportunities that we have there. But again, there's a lot of limitations here. And I think our hope with the study was that it can kind of spark conversations among the people who need to be thinking about this to figure out how we can translate these kinds of results that are very early into things that can actually improve healthcare and improve outcomes for millions or billions of people. I want to thank the team very much for everybody's contributions to the paper. This was very much a huge team effort, and as you can see on the archive link that there's a long list of authors. I also wanted to thank Shek in particular because she put together many of these slides. So thank you. And yeah, again, thank you for coming to the talk. I'm happy to answer any more questions that people have.
Awesome. Thanks so much, Karan. I think this was a wonderful talk. I guess before we move on to questions, let's give Karan a round of virtual applause. Great. Yeah. So yeah, let's open up the floor for questions.
Yeah, I have a question about the training data. Do you have an idea, what percent of the data related to the medical or clinical domain, and what are those data sources? What kind of data look like?
I'm not sure if I fully heard, but I think the question was what percent of the data related to the biomedical domain?
Yes, correct.
Yeah, I think I think a lot of the data sets were kind of spanning a bunch of domains. Maybe I can show this slide. I think the PubMed QA was the best data set for coverage of the biomedical domain, like biomedical scientific literature. Otherwise, I think the other data sets, for the most part, didn't provide too much coverage of the biomedical literature or biomedical domain. And I think that is an area in which we think future benchmarks could be quite useful.
Actually, I'm not asking about the data. I'm asking about the training data. It's the training corpus. So what percent of that was from, how much of the training corpus includes from the medical domain or clinical domain? Yes, what percent within this data?
I see. Okay. So yeah, so POM, so basically it depends which training area we're talking about. POM was trained on some data, flan POM was trained on some data, and then MedPOM was trained on some data on top of all that. Mm-hmm. So POM was generally trained, this is I guess the proportion of data. It doesn't look like there's an explicit training on the biomedical literature, for example, for POM. For flan POM, I also think this was mostly not the case. And then for our work, we did this kind of fine-tuning on a small amount of examples produced by clinicians, but we don't really think this is really comprehensive. I think in the future, and also already concurrently to our work, there's been some works that have been kind of fine-tuning on these corpora at a larger scale, and we think that kind of remains a big opportunity for kind of improvement of these models further.
Yeah, within this corpora, do you include something from like PubMed or the biomedical literature or anything from clinical notes?
To be honest, I'm not aware of the exact details of exactly what data was included in POM.
Yep.
Yeah, I had a question, Karan. So would the techniques that you did in MedPOM need POM as the language model, or could we use maybe substitute a different LLM, and what's the benefit, or how much of this is coming from POM versus the things on top of it, and what's your intuition on how people who don't have access to a lot of training resources or compute, basically, if they want to use a smaller foundation model, is something adapting your strategy useful or not?
Oh, absolutely. I mean, I don't think much of this is really specific to POM in general. I would say it's these techniques are more large language model specific than anything. So in general, all this stuff, especially the prompting stuff, is relatively easy to try with, for example, OpenAI's models that people have access to. And The tuning stuff, often researchers, including at Stanford, I think have access to the ability to kind of do tuning on fairly large models. All of this, I think, is not really specific to PaLM. It's completely agnostic, and yeah, we definitely have reason to believe that there's no reason that this is specific to PaLM.
That's awesome. Did you, by any chance, also do an ablation or something where you tried different language models to kind of see if like absolute performance increases or decreases in any of the axes in your evaluation? Because that'll be pretty cool to kind of look at.
So in this work, we weren't able to compare to any other baseline models besides PaLM, but we did, as you saw, compare between flan PaLM and MedPaLM. We also did look at PaLM itself, and PaLM itself was significantly worse, so we didn't include it in the kind of main evals. But yeah, we weren't able to compare to other like families of models in this work.
Gotcha. Thank you.
Cool. Any last questions?
I have a question about the MedQA. Are you aware like how difficult it is for MedQA, like for like a clinician? Or like, I guess the question is like, is it very surprising for a AI model to be able to reach like almost like clinician level accuracy on MedQA?
Yeah, so on MedQA, this is a data set that consists of questions, USMLE style questions from like step 1, step 2, step 3 exams that people take in the US. For reference, the pass mark on this exam is roughly 60%, very roughly.
Mm-hmm.
And the people who are taking this exam are typically students. I think the 95th percentile of performance on this exam is like 85%. On this exam, something around that. So hopefully that provides some baseline. If you're interested, I think you can find like percentiles of performance online, like for the step 1, step 2, step 3 exam.
I see. Sounds good. Yeah. So I guess it's I guess like you could say that MedPaLM is almost like a good student performance.
I wouldn't say that. I think there's a lot of limitations, but I think it's an exciting result for sure.
Yeah. Okay, sounds good. Thanks.
Karan, I had a question, which I'm happy to do after if it's getting long, but I'm curious if you can imagine any way that one could go back to the training set and see what the closest set of original training data is to the answer that's given by MedPaLM, with the idea of like being able to understand, where the information's coming from.
I see that is super interesting. So there are approaches for doing this kind of interpretability work. I'm not super aware of people applying them to large language models because that's probably quite difficult actually. But there are versions of maybe I can follow up with you on this offline in terms of sending you a paper. But there are some interpretability works that aim to kind of produce, given a training example, examples of proponents and opponents. Proponents being examples in the training data that promote the model producing that label on this question. And then opponents being examples in training data that don't promote that. So basically that would be like, if you're talking about like classifying dogs and cats or something like that, it would be like images in the training data that look like that and that were classified as dogs, images that look like that were not classified as dogs. That's the closest thing that I'm aware of to this, but I'm not aware of this being applied in large language model world.
Yeah, I can imagine. You have to have access to the whole corpus to do that search. But I mean, I think it could answer questions somewhat that I have, like that CU just asked. Like the USMLE is a very highly studied test. So as having gone through it myself, I can imagine in the age of the internet that those are much discussed on social media, on websites. There are study aids and books available for those questions. So I could imagine that if you got a good answer from that, you might be able to find that answer in an actual textbook someplace or a discussion. because as you said, it's like a subset. Like they're sort of, the textbook examples are really our textbook. They're meant to be a paradigm for it, and so there's kind of a limited set of things like you were alluding to, versus real world where like someone might present with a certain classic set of symptoms, but they actually have something else. But you're
Right.
on the test, you know, you're supposed to come up with, you know, a specific disease. But it would answer that, like maybe it did some interpolation and was very clever, or maybe it just found the actual answer, somehow stored it in its weights.
Yeah, this is a really great question. I think a great question for large language model research in general, like the extent to which, when we're doing well in these benchmarks, are we interpolating between existing things in the training data? Are we doing, and is that interesting, or are we retrieving from things that look very close to that? Yeah, I mean, I think this is like a super important question for like answering questions about like, are these models truly reasoning, or are they kind of not doing that? Things like that. I mean, personally, I think this is super interesting. And if you're aware of any work in this direction, I'd love to hear more from you.
Yeah, I'm not, but I kind of look to people like you or at Google, because it's just such a large data set. Like that it seems like someone with resources would be required in order to do that sort of project. But yeah, I'd be glad to talk to you about it.
Amazing.
And
Cool. I guess thanks everyone. I think we had a very lively and interactive session, and thanks Karan for the great talk. We'll be putting up this talk later on YouTube, and so if anybody has further questions, feel free to reach out to Karan, or you can reach out to us and then we can put you in touch with him. But yeah, thanks everyone, and hope to see you all next week.
Thanks everyone.
Thank you, everyone. Thank you, Karan.
Thank you, the organizers.
See ya.